So, we continue on the air jet texturing further, and what have we learned till now is that we have seen there are many essential elements in a air jet texturing machine, and their functions also. For example, drawing zone, which is a sequential process which must take place before the yarn enters the texturing zone, particularly if the filaments that is to be used as a raw material are POY or undrawn yarns. Then there is a texturing zone, which is the main zone where entanglements etc. would happen. Mechanical stabilization zone, where we believe that loose loops and entanglements will open up, entanglements become tighter, and so instability can reduce. Thermal stabilization zone, where also for thermoplastic fibers this can also help in reducing the instability. And we also learned something about the measurement of instability. So, we shall today look at the other ways of characterization of textured yarns. So, various characterization techniques that we may use, we have generally talked about the instability and the measurement of bulk. And we said that bulk can be measured in many ways possibly, but winding on a package and looking at a package density and the ratios are the one which have been used as a more realistic way of describing the increase in bulk of the yarn. So, hot water shrinkage basically is for any synthetic material which gets affected by the temperatures like thermoplastic material. This could be interesting. Otherwise, the shrinkage takes place because of the disorientation that takes place at a high temperature. So, the shrinkage in water or otherwise takes place either because of relaxation of molecules in a drawn yarn takes place at higher temperatures, that is one reason. If it is a non-thermoplastic yarn, so stresses that may have been introduced during the manufacture can relax, or in a hydrophilic system you also have shrinkage due to swelling. So, shrinkage can occur in any system, and you may be interested in learning about that. So, simply change in length and expressed as a percentage, one can express hot water shrinkage for any yarn, and we will try to see why it should be related in the air jet texturing. So, one way of finding out the bulk is what we described, but why a particular yarn behaves in a particular way, if one wants to learn more about it. So, you may like to measure 3 more parameters which in some way are related to surface that change takes place, particularly if you can watch it under a microscope. So, one is core diameter, you can express it, let us say micrometers, height of the loops, where is the average height. So, you will be looking at the average, and frequency per unit length, let us say number of loops per meter, for example, can also be measured if you really want to do some explanation as to how a particular yarn is behaving. So, this optical method in general will not really be used to describe the bulk, because we said last time that larger loops contribute to the actual bulk, in reality less than the smaller. So, if you watch under microscope, it will probably give you that should be much bulkier, but in reality it may not be, but this at least can be used to explain certain observation which may have been otherwise used. So, there is a textured yarn, edge textured yarn. So, what we are looking at is, so there can be a denser area which will be called the core, and protruding loops are the surface characteristics. And so, loop height for example can be measured. So, it is a hard work for whosoever wants to do. So, you measure in a particular length how many number of loops are there and what is their height. What it means basically is that you may be interested to learn that this particular thing is up to this point and this one is up to this point. So, you keep measuring these heights of various loops and then take an average out of that and express in whichever way, let us say micrometers can express. So, when you use any type of optimization process, some of these things would change. Then how many loops are there in a particular length, which can in a way tell the frequency of the appearance of loops in that, which will change if you change the overfeed, if you change the air pressure, and so some of these things can happen. So, we like to measure the tensile characteristics also like a stress strain curve. So, we said this is a bulk yarn. So, it may give a curve like this. So, what can you measure is the stress at break, elongation at break, and modulus generally may be expressed at 2%, otherwise 2% extension. A modulus can be measured and you can express. So, invariably as we said, the tenacity of the textured yarn may be reasonably significantly less than that of a parent yarn. And because a large number of filaments may not be contributing towards this resistance to motion at some stage. So, maybe good number of filaments are actually transverse to the direction of force, and so they may be weaker also. So, they can tensile strength may go down and sometimes extension also will go down. And if you look at the modulus of the yarn compared to the parent yarn, this modulus can also be relatively less. So, this may be a softer kind of a material, and so one can work around and determine that also. But tensile strength etc., we should be worried, not exactly worried, but we should measure it correctly because the loss could be quite high. This type of test can be performed on a normal Instron type of a machine, tensile tester. Only thing is, unlike the case of false twist texturing where this type of a characteristic was measured after the crimp or decrimping, after decrimping. So, you had put enough load to decrimp the yarn and then do the stress strain characteristics. But here we just have to ensure that you are putting it straight and not loose, that is all. So, now we look at some of the factors which would affect all the properties of the edge textured yarn. So, we have seen a complex machine. So, there can be raw material variables, what material that we are wanting to texturize, machine variables. So, you have machine, there are many parts, many zones, all of them can play some role, and actual process variable which are in the texturing zone, which you have probably more control. Raw material you may have control, you may not have control, but you should understand what could be the effect, and how the machine behaves also must be understood. So, we said that this is a mechanical process and the characteristic of the material should not be so important. We were looking at the chemistry part of it, that should not be important, but it is not true. So, we are not looking at the thermomechanical setting of the material where molecules will be changing their configuration during this process. That does not happen, but whatever molecule that you are feeding, for example, you are drawing and then feeding, drawing at a higher temperature and feeding, has a chemistry and has a history. And what kind of history? See, this was one of the things which also was not understood in the beginning, and people thought whatever material you can use it for false twist texturing should also be good enough material for this type of process as well. And general belief that you put anything, everything will happen was also one thing. But we understand that based on the chemistry, the rigidity of the fiber can change. Like we said, the modulus of polyester may be higher than nylon in general because of chemistry, aromatic ring, and if nothing else, this process involves bending of a filament and loop formation. Anything that can affect the bending, that means the rigidity of the material, will affect. And if polymer type also affects the rigidity of the material to bending, then it should also affect. So, that is the way it is. Of course, we are not interested in changing the internal morphology during the process of texturing. Therefore, we cannot completely say polymer type will not have any effect. You can texturize, but it will have an effect, we must know if it is. Under the same process conditions, 3 different kinds of polymer fibers may not give you the same result. The modulus, as we said, determined by the chemistry or determined by the pre-texturing conditions that you have had. If that changes, this can change, because this modulus of the raw material is going to be related to again bending rigidity in some way. And so, a material with a higher modulus versus the material with a lower modulus will give you different characteristics of the edge textured yarn. Now, this was an interesting part which was a great learning for the people who are working on edge texturing. The fineness, that means the denier if it is finer versus the denier which is coarser. Now, we are looking at the individual filaments for that matter. In the case of false twist texturing, we had said that if the individual denier is higher, you get a better textured yarn. Here also they use the same material and they found the things were not really working out well, because again a fine fiber bends very easily and your aim is to make loops and do various kinds of entanglements. So, this is absolutely opposite to what false twist people wanted. They were happy with 2 denier, 3 denier individual filament deniers, or 6 denier also they were very happy. But if you use 6 denier here, results were not good. So, here it was very simple that if you have finer denier, it can bend very easily, it can make loops very easily. And remember, the total time available for all this process is much less than the false twist texturing also. So, if any resistance is created during this process, then it will be affecting. So, this is almost opposite requirement, and because this was not understood initially, so it also took some time for making a better yarn which would be successful and give a good final product after weaving or knitting. So, fineness. So, finer is the fiber, individual fiber, better is going to be the texturing. This also became interesting, the number of filaments. So, it can be related to fineness. So, same total linear, if the number of filaments are more, all of them have a probability of getting entangled, formation of loop, increasing the bulk. So, here the larger is the number of filaments, it is likely that you will get a better yarn. So, when you feed more than one yarn together, number of filaments become more. If the linear finally is acceptable, then it would give you a better textured yarn, because ultimately what we are doing is we are dependent on making loops, forming entanglements which should be as good as it goes. So, this is one. So, this is all material. Then the cross section. The cross section, if it is circular or it is triangular or it is rectangular, will definitely have different bending rigidities, even if the linear is same. And so, we can expect different results if the cross section is changed, because we are only have air or a compressed air within a jet which has to create turbulence, and within that turbulence if something happens, this is going to affect. So, while we were saying that we believe that this process is simple, mechanical, nothing to worry about, feed anything, get anything out of it, was not so true, and therefore, various factors do affect, and you therefore should be able to smartly decide as to how will you handle such material. For example, this material bending in this direction is easy compared to if you try to bend across this. And so, rigidities will definitely play a role, and dimensions, everything, density is same, linear is same, number of elements same, fineness is same, modulus of the material is same, and still because of cross section you will get different results. Then there is this inter-fiber friction. Lot of people published lot of work on friction itself, because what was believed was that the way the entanglements take place and the way the loops are kept in position is definitely related to fiber friction. So, when you stretch, the loops will not open easily if the fiber to fiber friction is higher. This was generally believed. If suppose somebody asks this question, that you have been given a material, what would you like the friction to be, less or more? Just a question. Yeah? More?
Less.
Or less?
Less.
Less. Why?
Friction विशिष्ट रूप में समा.
So, we will not answer this question, think about it and do better argument. The final product that we have is held by only mechanical reasons, and friction is one of them. Once the entanglements have done, and then this yarn has to be used in different places. So, this actually was a matter of good discussion, and I hope some of you will pick up when for the term paper, fiber friction itself as one of the research topics. So many papers were published on this. So it was not as easy as just talking here and finishing it off. Applying different levels of finish, reducing interfiber friction, increasing interfiber friction, all that was thought of and done. So we'll leave it, and this question you can answer at some stage. You can keep noting that would you want this friction to be higher? Obviously where? In the raw material to begin with. Machine variables are the most important thing which people learnt at a later stage, that it is not simply something where compressed air is coming and yarn has been overfed into it and everything will happen just like that. So good amount of work has been done by machinery manufacturers, as well as research was done in the education institutes also, to see what kind of a design should be there of a jet, so that you get two things. One, good entanglement. And if you can get good entanglement, then your instability becomes better. You cannot say make a very bad yarn and then keep on doing mechanical stabilization, everything will open. You may get something, but if 50% loops are open, then what's the yarn that you are giving to someone? Or take the bad yarn and start doing thermal stabilization, feel everything will be nice. No, you have to produce a good yarn to begin with and then improve upon it. So, to understand exactly what kind of a jet design, you have to understand what is actually happening. And this appeared to be a complex process. It was not so simple. Look, just put some kind of orifice, put something from there and just go back. So good amount of work has been done. As far as jet is concerned, not many companies make jets. Any company can make the texturing machine. A winding zone, a creel and a hot heater and a mechanical stretch. It's very simple. But jet, everybody doesn't know. So you get the jet from somewhere and add into machine and work around. So jet design became, obviously it's not your hand, but you can probably, if somebody tells you that this jet is good enough for this type of a range of linear, this is good for the other range of linear. So one was how good the entanglement takes place, which is the most important thing. And the other is how much air is it consumed. So you say air is free. No, compressed air is not free. It's just like opening a tap and it just goes on. The total energy consumed is very high. It's a very simple process, but it appears that even if you don't heat anything, you still are compressing the air and just blowing it off. So what kind of design would be which consumes less amount of compressed air and does a maximum job? Those are the things which people had to work around to understand. Instability was an important thing, and therefore some people actually said that why can't we do pre-twisting the yarn and then feed, not just drawing and feeding. Pre-twisting the yarn and then feed. So what will happen? Well, the twist will untwist, some loops will form, and as it comes out, the twist will flow back and things will become tighter. And they got some success also, but not commercial success, scientific success, prove a point. But when you want to twist, real twist now, not a false twist, that means you are making a process, a batch process. Continuous process is not there. So there were difficulties. And so jet design became an important material, important machine variable. Then when they designed, they also created certain control features within the jet. It's called setting, using a particular setting in a jet itself, based on what denier you are using, what kind of a number of filaments are using, two types of fibers, and whether a product is coming good or not, can the turbulence be changed. So, they have dials which can control the effectiveness of a jet, same jet, by changing the setting. So, it became interesting. What means the chamber where things are going to happen, the velocity of the air, is it going to increase or decrease? That type of a thing can happen by some of these settings, and therefore, this became important. And that took time. That is why, while the process was understood even almost the same time or even before the synthetic fibers came, but bad results. So, it took time for people to understand the process and then the design. So, material also was different, and obviously, this small heart of the machine also was the complex system. And of course, then they realized that if twisting is not to be done and so on and so forth, raw material that is available. So, you had a drawing zone, what is to be done before, mechanical stabilization zone, thermal stabilization, all these were added to improve the performance. But the moment they are there, then if you have mechanical stabilization 3% or 5% would give you a different yarn, or a drawing for that matter, room temperature drawing, or temperature 80 degree or 90 degrees if you do, it can change some of the raw material characteristics, and things can happen. And later on some attachments of course are there these days. One of the interesting attachment which people may find is that people say, well, you are saying that this material is going to be behaving like a spun yarn, but spun yarn has hairs, individual fibers which are protruding. Here you have loop. So, how can a loop be equal to a hair? So, yeah, it is not exactly, but quite good. So, people say, why not we cut the loops, and they become hair. You have got good entanglement and I am cutting loops. It is a different, you can have those kind of attachments also. And of course, in the heater, if fumes are coming, they have to have vacuum extraction, all those type of things one may have. The process variables, if you have a draw zone, you can have a draw ratio, and a temperature of drawing itself may become maybe secondary parameter, but if you keep changing these, you will have different material. One has to see why will you change that, because you would like to draw material based on the residual draw ratio and use a temperature which is optimum. So, maybe that is how you will push it, but if somebody keeps changing this for whatever reason, the denier is too high and you say, well, I will increase the zone temperature. So, things can change somewhere else also. The only thing which you may not do is the time. I have not mentioned time. Otherwise, how much time you give during the drawing can also be a factor. That means machine speed. But if this is a process which is happening in sequence, so you probably will appreciate the more important parameter is the time required in the texturing zone. You will be more concerned about the machine speed variation, so that the time available in the texturing is controlled, and because you cannot have independently running machine speeds. So, machine speeds will not be decided by the time required for completing drawing. You will have to do something else, because machine speed will have to be decided by that. That is the most important zone. So, if we come to the texturing zone, so obviously you have air pressure, you have a control, complete control, there is no issue in that. Whatever material that you use, you can keep changing the air pressure and see the effect on parameters that you discussed before, characteristics of a yarn. Overfeed, the two important things which will change quite a lot of things. And yarn speed means the machine speed which determines the residence time available in this zone. And how much time did we say we normally when we are having? So, you are looking at 2 decimals, so 0.01, right, or 0.1 or less than that kind of a time that we are having. So, this will be an important step. So, you decide your machine times. We have written here something called a water amount. This process is supposed to be a dry process, like false switch texturing, dry process. But if you remember, we had mentioned in that line diagram that there can be a water applicator. So, effect of adding a bit of a water, obviously good water, not a hard water. So, you have to have water, was seen to have affected the characteristics of the textured yarn. We will talk about it. Some more details you can do in your term paper. So, amount of water that you add can also be one of the process variable. But if you look at completely, once we decide the time, machine speed, these two become the very important parameters which you have control. So, the other variations can also be there. If you think that improvement is required more, so mechanical stretch 3%, 4%, 4.5%, 5% stretch could be a variation, and one can see what happens, heat stabilization temperature and the overfeed that you give within that could be the thing. Again, we have not written time here, because the speed of the machine and therefore the time is determined by the texturing zone. Then you have winding zone, in winding also you may have give some tension. Hopefully, this is not going to make much of a difference if you have already gone for mechanical stretch and heat stabilization, but you normally do a bit of underfeeding, so that tight packages are made. And if replenishing has to be done of a spin finish oil, then that also may be important, because during the heating, if at all heat stabilization is done, you would probably have to replenish. And one of the reason is that the spin finish which has been used on a POY, which mostly also goes for false switch texturing, has already been decided. So, now saying that for drawn yarn I will have a different spin finish, for air jet textured yarn will have a different spin finish, may not work. So, you may actually have a yarn which has spin finish which part of a component evaporates, and so you will replenish it at a later stage. Not very critical, but if you have a bad one, then everywhere there will be problems. So, we now look at some of the important process variables and their effect on again some of the important properties, not every property for that matter, but one can think of. So, effect of overfeed on stability, instability. So, we have overfeed, let us say, which may be expressed as we say as a percentage, overfeed 20%, 30%. This also is in percentage. So, we increase the overfeed in the texturing zone, And instability is one of the interesting parameters that we have. What do we expect?
It decreases instability.
Instability will decrease. Let's go here. So you're saying it will decrease? So I call it curve number 1. Anyone else? Any other response? Or we are happy with this? Any no response? All right. So if there's no response, we like it to be explained as to why do you believe that it should decrease.
When the overfeed increases, the loops will become more entanglements will be there.
So what you're saying is when your overfeed is there are more entanglements. So, happy with this argument? So, what is the other argument then? So, actually, what has been found is this happens like this. So, when you give more overfeed, then obviously more filaments are available. They make all kinds of loops, they will make more loops maybe. But because of this itself, the entanglements are not so good. Why? Because when we say we are increasing the overfeed, we are assuming obviously that pressure is constant. So, whatever forces are available to do the job remain the same, but material to be handled becomes more when you are pushing more material in the same zone. In fact, if you keep increasing, it can become so bad that you just will see it just opens, starts opening. So, we are obviously concerned about it. So, instability will increase, or reverse of it, stability will decrease, but we measure only instability. So, you will probably go up to a certain point and then say, well, not beyond, or change the other parameter. So, we look at the effect of overfeed on bulk. Remember, the bulk is measured based on the package density, okay? Of the parent and the textured yarn. What kind of a effect that you want to see a trend? So, what do you expect? Yeah, it increases. All right. Can it decrease? constant. Okay. So, before we answer this question, let us answer this question. And the question is, what would happen to the structure of the yarn, which now we know can be expressed as the diameter, core diameter, or the average loop size and the loop frequency. What we are doing is, obviously, the air pressure is constant, machine speed is constant to the extent that the whatever the overfeed takes care. So, we finally have the same kind of speeds, similar. What do you think will happen to the core diameter? Diameter of the core when you just overfeeding, it should decrease, increase. All right, so good, the core diameter increases. What would happen to the loop size? It should also increase. Very good. And what should happen to the loop frequency? Decrease when you increase the overfeed. If we increase the overfeed in an air jet texturing process, keeping the constant air pressure, the loop frequency should decrease. Okay? It also increases. So, because more yarn is available for inside the core, outside the core, number of loops that can be formed, because more yarn is available, it is not that large loops are also being formed, but more number of loops are also, number of loops are also increasing, size is also increasing,
If size increases, then frequency should decrease.
but number is increasing also, number is also increasing, because length being given is also more. You have 10% overfeed, then you have 20% overfeed, you have 30% overfeed, 40% overfeed. So, excess length also of the filament is available, which can bend. So, they can bend. You may not like them, you may not like the yarn as such, because instability is not good, but this fellow is trying to just keep increasing its bulk. So, the effect of increasing the overfeed is to increase the bulk. Otherwise, how would you come to this conclusion? Everybody said this. So, bulk is increasing. Obviously, there may be some larger loops also, which may not be contributing, but some smaller loops are contributing, which may also are generating. That means, if the frequency increases of the number of loops increases, average size increasing, core diameter also increasing, because it may not be very compact, but whatever you call as a core, which is other than the protruding loops, is also increasing, because you get some space for them, some may be inside, some may be outside, but more of them are being formed. So, core diameter can increase. And so you are right that this is what you will expect. So, in a sense, it is good, bulk is increasing, but instability is also increasing. So, after some time you will say, well, I cannot get more unstable or can get yarn with more instability, even if bulk is increasing, will not really like that process. So, maybe we will stop here and take it next time.